Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we will discuss some terminology which is used in reaction radial flow turbine. So in our last lecture, we have seen that reaction turbine and radial flow reaction turbine. And in that also we have discussed about the inward radial flow turbine. So now we'll see some terminology which is used in this reaction radial flow turbine. So the first one I'll consider here a terminology which is known as speed ratio. So the speed ratio actually, we can write the speed ratio in terms of, we can say it is the ratio of that velocity of the turbine or velocity of the blade, or we can say tangential velocity of the blade with respect to the velocity of jet at the inlet condition. So the speed ratio also can be denoted by phi. Sometimes it will be denoted by phi and sometimes it will be written in KU. So some books it will be given in this term and some books will be given in this term, but mostly it is to categorize into like sometimes the speed ratio will be calculated for turbine and pump also, but in general we can write both of the terminology, and the ratio of this speed ratio, like this one, we can write in this way: E1 divided by root over of 2gh. E1 root over of divided by root over of 2gh. E1 equal to here the blade speed, or you can say the tangential speed of the blade. So this is it inlet condition. So we can write only U also, but though I have written the E1 here, so we can write this is tangential velocity of blade. So this is nothing but tangential velocity of blade or wheel, we can say. Suppose let wheel, though it is given U1, so we can consider this is at inlet condition. Only thing, if it is given only U, then no need to write at inlet condition or outlet condition. And similarly, H is there. So H equal to, we can write this is the net head. This is net head. And this U also sometimes is called like, only the speed of the turbine, or speed of the blade also. So this one actually also can be written in some books, like phi equal to will be given only U by V. Okay, this V is nothing but the inlet velocity, the jet velocity at the inlet condition. And when you consider the theoretical velocity of this jet, so that can be written in this form also. And the value of this speed ratio is to vary between, 0.6 to 0.9 in this ratio. And basically it is a dimensionless parameter. Yeah. The next one is, we can write this is flow ratio. The next one is flow ratio. And this flow ratio is to denoted by two terminology again. One is psi, and sometimes it is to write in terms of kf. And this is defined as, that flow ratio is defined as the ratio of velocity of flow. The ratio of flow velocity at the inlet condition we can consider. Similarly, we can write this is Vf1. Okay, Vf1 to the velocity of a given fluid. So that can be taken again, same thing, 2gh. As I told you that if I can write in this way, E1 by, suppose V1 is there. Okay, so both are in the inlet condition. So phi equal to what you can write? Only the velocity of the blade or tangential velocity of the wheel or blade at inlet condition with respect to the velocity of a fluid which is given. So similarly here also the same thing, only we have changed the, on behalf of tangential velocity, here we have written the velocity of flow. So again, same thing I can write here, the Vf1 equal to, I can write this is velocity of flow or velocity of fluid, or we can write this is the component of absolute velocity. This is can be written in such a way that this is the component of absolute velocity in vertical direction. If you remind me, let me tell you, suppose this is the blade is there, and the impact of jet on the blade in this way. Okay, and this is v1, and this is called absolute velocity. And if I resolve this velocity in terms of x direction and y direction, that can be, y direction can be here, or I can give it here. So this is our actually vf1, and this is our actually vw1. This one we have already discussed previously, just I'm giving a hint on this. So this is actually flow velocity. That's why I've written the component of absolute velocity can be also written. And the value of psi is varying between 0.15 to 0.3. Okay, so this is another terminology. And here again, same h is there, that is now net head or head of the turbine can be written. Yeah, the next one is discharge of turbine. The next one is discharge of turbine. So we know that the discharge formula actually, so discharge is to denote by capital Q. This one we know that. And so the discharge can be defined in this way, that Q equal to, we can write suppose A1 V1, or we can write like, you know, A2 V2. So this A1 V1, this can be written like, you know, yeah, area. So area of the jet, and this is V1, velocity of the fluid. So this one we can write again A1 VF1, and this one can be written like A2, and this is VF2. 1 means inlet condition, 2 means at the outlet condition. Suppose if I consider here, this is 1 and this is 2 at this outlet condition, the velocity triangle will be like this. Okay, so here the discharge of the turbine through a reaction turbine, reaction radial flow turbine, can be written in this way, Q equal to this one. And these things I can write in this way. Again, let me write, this is Q equal to, I can write area in the place of area, I can write this is pi d1 and b1, pi d1 b1, this is area, and vf1. Okay, and similarly I can write, this is similarly I can write one more terminology, this is inlet condition, and for the outlet condition also we can write like pi d2, and this is b2 into this is vf2. So as I told you that d1 is nothing but diameter of the runner. So the diameter of the runner at inlet condition, at this point, what is the diameter is there? If I take a center point of this, from this center point to from here, how much distance is situated here? From here to here, how much distance? And this is outlet count. So d1 we can write, that is nothing but diameter of the runner at inlet condition. This is diameter of runner at inlet, like through which the liquid is flowing, or the liquid is entering to this one. Similarly, this one we can write diameter of runner at outlet condition. And similarly, d1 I have written. Now next one is v1. v1 is nothing but, this is actually width of the runner. Width of runner at inlet condition. And similarly, already vf1 already I have told you that velocity of flow at inlet condition. So this one you can write, this is can be written here, velocity of flow at inlet condition. Similarly, we can write this is b2 and vf2 also with respect to outlet condition. These are the terminologies are there for this discharge. Now again I can write this one actually. If suppose this area part, let me tell you first area part. The area actually, if I consider the gross area, I can write AG. AG equal to what I'll write here? Pi D1 B1. What I've written here, the area value here. Now thing is that if there are number of blades are there, not a single one, if there are number of blades, n number of blades are there. If suppose n number of blades, actually this is n number of blades. If n number of blades are there and each blade is having a thickness T, each blade is having a thickness T, then how to write that one? So here in this case we can write that area of the blade, we can write this is N into T into V1, N into T into V1. And here this is our area of the blade. Now what is the effective flow area? Like at which effective flow area, in the sense this is the gross area and this is blade area. Now if I want to calculate the effective blade area, so I can write what is the effective flow area. Actually you can write this is effective flow area can be written area effective equal to what is the total gross is there, area of the gross minus area of the blade is there. So this one minus this. So we can write this is, as I told you, this one pi d1 v1 minus here it is n t v1, and here if I take a common of b1, if I take a common of b1, I can get here it is pi d1 minus n into t. So this is actually, sometimes it will be given the thickness of the vein will be when you consider the thickness of the vein, thickness of the blade we can say, or vein also we can say. So the area through which the flow takes place, so that can be written in this way. Okay, and so here we can write q equal to we can write this is pi into d1 minus n into t, and this is v1 is there at inlet condition we are considering, and this is vf1. So this can be the equation for this. The next one is the head. The next one is the head of the on the turbine. The next one is we can write head on turbine can be written h equal to, this is P1 by, we know the formula, P1 by rho g plus this is V1 square by 2g. Okay, and this terminology actually is to can be written, this is pressure head. This is pressure head and this is our velocity head. This is velocity head. So here we can say this is P1 equal to the pressure at the inlet condition, V1 equal to, already I told you that velocity at the inlet condition. So this is about the head at the inlet condition. Now one thing maybe in your mind it will become like, why this required and what is the conclusion from here actually. If you see this like what we have written here, this is the final equation, correct? Not this one exactly, this is the final equation what we got from the like discharge is there. Now yeah, so what I can say that if more blades are there, if we have one more things I can say, if more blades present, then we can say that more area covered. More blades is there means more areas are covered in this, more area are occupied. Now similarly, if more area are occupied, then we can get less discharge. We can get here less discharge here. Similarly, we can say if the blade thickness, the thickness we have considered, so if the thickness of the blade is more, then which is reduce the effective area. Thickness of blade, if it is more, then obviously which will reduce, it will reduce the effective area, reduce the effective area. Okay, these are things we can get from here. Okay, now we have discussed about the head. So head part is completed, that P1 by rho g, this is pressure head, this is velocity head, V1 square by 2g. Similarly, we can write that yeah, one sometimes will give a radial discharge. Sometimes one more will be given, this is radial discharge. In the questions it will be given, let's consider that discharge of the fluid is radial. So this exactly means that absolute velocity the absolute velocity V absolute is when it is with a tangent to the wheel is 90 degree. When radial discharge means this V absolute is 90 degree. This one actually, when you see this triangle, this is our V absolute when it is coming out. Actually, when this liquid is coming out from here, this is our V absolute. Okay, V2, and this is your relative velocity. This is your flow velocity. I hope you understand this one, because if you don't know this one, you can see our previous lecture. There I have explained already. So this one, if radial discharge, in the sense this V absolute is of this one is considered as 90 degree. Okay. That means the absolute velocity of the tangent is will to be 90 degrees, so that the component of the wheel velocity will be 0. Obviously, the component will be, it will come here, that will be 0. So 0 means we can say the radial discharge at the outlet condition. That means the beta will be considered as 90 degree. Not this one 90 degree. We can say that it will be the absolute velocity with the tangent on the wheel. It should be 90 degree. So tangent where? Tangent is this one. Okay, the tangent will be this one. Now it is angle is there. Okay, this beta angle. That means it should become perpendicular, this 90 degree. Okay, this one, that's why I've written when it will be 90 degree, then we can say that is beta equal to 90 degree. And so for this, we can write this is VW2 will be in this condition will be 0. And at this condition, our alpha angle will be alpha not, we can say that beta angle is 90 degree here, this outlet point. And similarly, at the inlet condition also, if you want to consider here, that can be taken this VW2 0 and beta equal to, and this is 90 degree. That's it. Yeah, the next one is if suppose there is no loss of energy. Suppose no loss of energy. If there is no loss of energy, then when it is possible, when the water flows through the vent, then we can write when there is no loss of, if there is no loss of energy, then we can write H minus this H minus V2 square by 2G. V2 square by 2G equal to, we can write this formula like 1 by G. This is VW1 E1 plus minus VW2 U2. This is when there is no loss of energy is considered. This will be the equation for that. So these are some terminology which is used in the reaction radial flow turbine. Along with that, also we can consider, as I told you, that ratio of width. Okay, actually the number of thickness that is actually, we can say the number of runner or how many number of blades are there, we can say. So one more terminology is there, N equal to, it is B by D. So the ratio of width, this is actually, we know that width, we already told you. So the ratio of width and to the diameter, runner diameter. Okay, to the diameter of the runner. This is the width of the runner, and this is width of the, diameter of the runner. Okay, that can be written in terms of N. Okay, sometimes we need to calculate this also. So this can be, and the value of N will be in the range of 0 to 0.1 to 0.45. Okay, and remaining all things I have told you. Yeah, one more is there, tangential velocity. The tangential velocity, sometimes we used to calculate U equal to pi d n by 60. And when it is given, U1 will be given, then we can write this is pi d1 n by 60. And so for U2 also, you can write like pi d2 n by 60. So by this way, we can calculate the tangential velocity, this one. And some other terminology is there. If you see the previous lectures where we have discussed the velocity triangle for inlet and outlet conditions, that things also we need to remember in this. So I hope you understand this lecture, like what are the terminologies are used in the reaction radial flow turbine and how to utilize this. And basically we need to remember this formulas, what I told you, like speed ratio. Sometimes the questions will be given based on this, and this is our flow ratio. And discharge, already previously we have studied this one, but here finally we got this discharge value when it is like, thickness is given, number of blades will be given extra, and this is head of turbine. This is radial discharge. Already we have discussed previously, just I have reminded you this one again. And this is no loss of energy. So I hope you understand. Still, if you are having any kind of doubt, query regarding this, you can give a comment in the comment box. Thank you all.